So this is the second half of the video that lets you learn how to calculate enthalpy theoretically. You've already seen two different ways: bond energy calculations, which you learned during first year chem, and then Hess's law, which kind of takes various equations and lets you add them together to eventually get the target equation that you're looking for. Well, this third method is called enthalpy of formation calculation. So delta HF for formation. It's really the amount of energy that's associated with the formation of a particular compound from its elements. So for example, H2 gas plus O2 gas giving you H2O in liquid state or gaseous state. The energy associated with each of those is going to be different. So in this case, it matters what state you're looking at. So you have to be careful. You have to be observant of states. Since enthalpy is extensive, it depends, the energy content depends upon how much stuff you have. We use typically standard enthalpies of formation, which are collected under the conditions of 1 atm and 25 degrees Celsius. So all the numbers that you are going to see are delta H of formation standard. So that's what that little zero means. That little zero is actually read as a naught, not K-N-O-T, N-A-U-G-H-T, I think. Anyway, that's the standard condition. That's what the little zero means, or the little circle means. It's not a degree. So under these standard conditions, how much energy is associated with forming a compound, 1 mole of a compound, from its elements. So here you've got a list of some of the standard enthalpies. Notice that if a substance is in its natural state, it's got an enthalpy of formation of 0. Solid, magnesium; gaseous, nitrogen. Anything that is in its natural state didn't take any energy to form it. That's the way it is. So we give it a value of 0. But if it's not in its natural state, for example, O2 gas is 0, but ozone is 143. Carbon and graphite, that's considered the standard state, versus diamond, which has an enthalpy. So again, state is important. All right, so let's take a look at an example. So I want to determine the heat of reaction for this particular, I want to determine the heat of reaction for this particular substance using the standard heats of formation. So there is a nice big list of standard heats of formation in Appendix C of your textbook. Appendices are in the back of the book. So what am I going to do? I'm going to take all of the energies of the products, all the heats of formation of the products, in this case there's only one, and I'm going to subtract all the energies of the reactants from it. I need to consider how many moles, and I need to pay attention to the state to make sure that I'm getting the right value. Now, this is a reaction where you are taking products minus reactants. You are going to see this a lot. If you remember, bond energies was reactants minus products. It's the opposite of everything. That's why I really strongly suggest that you do not learn that equation and just think practically about it. To break a bond, I have to add energy. That's endothermic. To release a bond, or to form a bond, I release energy, so that's exothermic. Whichever one is bigger is going to control your sign. This one isn't quite so obvious, so learning this equation is much more important than learning the bond energy equation. So products minus reactants. So what am I going to do? I've got to take 2 moles of SO3 gas, and I'm going to subtract the 2 moles of SO2 gas and 1 mole of O2 gas. Obviously not the actual materials, but the heats of formation. So pulling the numbers off of Appendix C, SO3 is a negative 395.2. SO2 is a negative 296.9, so essentially I'm adding this together. And then oxygen, natural state, 0. So when you add everything up, you do wind up with a negative 196.6. So this process is an exothermic process. SO3 forms and releases energy from SO2 and O2. All right, another example. Here's one where we're taking kind of combining Hess's law and standard enthalpies of formation. We don't know what the heat of formation for CS2 is. Nowhere are we able to find the value for graphite or the value for rhombic in order to get the value of CS2. We don't know, well, these two technically are 0 heats of formation, so we need to know what this is. We're going to do it from equations that we already know. So here's carbon reacting with oxygen to produce CO2. Here's sulfur reacting with oxygen to produce SO2. And then we can get CS2 to react with oxygen to produce those same two sets of gases. So the fact that we've got these two gases associated with more than one equation is why we're going to use kind of Hess's law idea to figure it out. So here's our target equation. Carbon plus sulfur gives you carbon disulfide, liquid form. So I'm going to take these equations. Carbon's on the reactant side. That's good. Sulfur's on the reactant side, that's good, but I need 2 of them. I only have 1 up here. I need 2 down here, so I'm going to multiply the whole thing by 2. And then CS2 needs to be on the product side, so I've got to flip this last equation, which means I'm going to change the sign of it. You go through and cancel out everything that is a spectator, so to speak. You wind up with the target equation, and therefore a value from adding all these guys up of 86.3 kilojoules. So we're kind of combining both the heats of formation and Hess's law idea to figure this one out. All right, and here's the big ideas that the calculations are supposed to be showing you. So my timing isn't so great on this video. All right, last idea, enthalpy of solution, delta H of solutions. You saw that a lot in first year. We dissolved things and measured. Sometimes it got hot, sometimes it got cold. We never really talked about why that is. So here's your chance to see it. So some common salts dissolving in water, you can see some of them are exothermic, some of them are endothermic. The magnitude varies a whole lot. So, quick question for you. Which substance would you want to use for melting ice? Do you want to use things that are exo or endothermic? Hopefully you know the answer is exothermic. These are going to generate energy. Second question, you've got a cold pack that you're going to make. Which ones are best for that? Well, if these are going to create heat, these things are going to take heat in, and so these would be best for creating a cold pack. Why do some create energy? Why do some absorb energy? Here's what's going on. There's a couple different things that has to happen. First, you have to break up that crystal lattice. So since you're breaking these bonds apart, breaking bonds requires energy. I'm adding energy to break up those ions. Once those ions are broken up, then I have to hydrate the ions, surround them with water so that they're dissolving, which means that I'm going to form bonds with the hydrogens and oxygens of water and the ions. In that case, this one, forming bonds, creating something more stable, releases energy. So the difference between how much does it take to break up the lattice energy and how much do you get out by forming those hydration bonds is going to give you your delta H. Sometimes it takes more energy to break the ions up. Sometimes you get more energy out when you hydrate the ions. So it really depends. Bottom line is the heat of solution is going to be the addition of the two steps because one of them is endo, one of them is exo. Whichever one is greater is going to give you the overall sign of your delta H. All right, so there's the end of the slideshow. Now you have all those ideas that you need to go on and do a little bit of practice to calculate delta H theoretically in the different ways. Good luck.